Clicker, thank you. Okay, so welcome everybody, and thank you very much for staying around for this, although I'm sure that the delicious scones that you were offered at the interval had nothing at all to do with your decision to stay around. I'm going to talk about, well, you can see the title up there, Solar Flares and Superflares, and it's also closely related to the opening, the unveiling tomorrow of the new installation at the Multiverse, which has a flare in its title. Normally, when I give this talk, I start off with a stock image of the sun, of a sunset or a sunrise, just to illustrate how fundamental the sun is and how beautiful the sun is as part of our existence. But inspired by Jocelyn's presentation yesterday of the universe in words and pictures, I thought I would put this one in instead. This is one of Munch's happier paintings, I think. It's called The Sun Rising. And it was painted for the University of Oslo. It used to hang in the aula of the University of Oslo, and it's colossal. It's an enormous painting. It's now in the Munch Museum in Oslo. And it's interesting that it's in Oslo, in Norway. You know, these northern latitudes, we have an intimate relationship with the sun. We enjoy it for almost 24 hours a day during the summer and almost 6 hours a day during the winter. And also, in the northern latitudes, there's a lot of influence that is seen very directly of the activity of the sun, i.e. the northern lights, and Jim's going to talk about this later on. But I like this painting because I think it captures both the dominance of the sun and the dynamics, the dynamism of the sun. I remember seeing this for the first time as a PhD student and trying to work out what all of the bits could possibly represent. In fact, I think they just represent glory. I think that's what it is. So there we are, Munch, 1911. So that was a little bit after this kind of episode here. This is the Victorian Internet. Although, actually, if you know anything about your costumes, you'll realise it's not, because the ladies are all wearing bustles, so that puts it in the Edwardian period, but I didn't have a picture of the Victorian Internet. 1859. Was the kind of time when telegraph was taking off and messages were being communicated by telegraph. And there are events, there are reports, which again Jim will go into in more detail, of some dramatic happenings taking place in telegraph offices around the world. Sparks, fires breaking out, happening around the same time as dramatic auroral displays, unusually bright auroral displays. Coincidentally, or maybe not, there were observations made by, we heard the name earlier, Carrington, the son of the brewer, of a rare phenomenon on the surface of the sun. Carrington drew sunspots, as Yvonne mentioned. He went out daily or whenever the weather would permit and drew the positions and the sizes of the solar spots, and he actually rendered them really rather well. And this is a sketch which is published in the monthly notices of the Royal Astronomical Society, a journal which continues to these days, to this day. And you can see some objects in there that you might recognize as the dark central part, and then there's a kind of a paler region around the end. But what I've done is indicate in bright red 4 lozenge-shaped areas. And Carrington remarked on these unusual brightnesses, these unusual phenomena, unusual brightenings taking place in the core of a spot group. Now, this was in the days before any photographic technology was applied to the sun. And so, as a scientist, he wanted to get somebody to verify it. So he ran off to find his assistant. But by the time they got back, he reported sadly that the phenomenon was greatly diminished. However, it was independently observed by another astronomer. And this is, to our knowledge, the first recorded observation of a solar flare. This was an optical light in the white light part of the spectrum that Annika mentioned, and also Yvonne. And these were bright optical flashes likened to the star Alpha Lyrae. very bright blue flashes. And this is the first recording, the first drawing that we have of a solar flare. And somehow, it was related to this and to this. Now, I'm not going to go there. I'm just going to talk about the flare part of the story. So let's go back to what you're becoming familiar with now, a movie of the sun. This is a movie of 1 year of sunspot data, and you can see it's speeded up enormously. It's speeded up by a factor of 15,000. And what you can perceive very easily is, well, first of all, that there are spots. Secondly, that they're coming and going. Also over, the period of one rotation, which is about 25 days. If you look at the equator, it's about 25 days at the equator. And the whole thing gives the impression of being in a state of constant motion, with spots growing and merging and twisting around one another and disappearing. And we now know from Innika's talk that these are sites where the magnetic field is very strong. And so we have a kind of expectation that as the magnetic field emerges and seems to break and twist around one another, that there's something pretty exciting happening in the atmosphere of the sun at the same time. So this is an optical image. This is the kind of thing you could make from a ground-based telescope. This was, in fact, made from space from a satellite called the SOHO, Solar and Heliospheric Observatory, which has now switched off this particular instrument, but has been replaced by something better. And let me just reiterate again what Innika said in response to a question. What we were looking at was visible light. The radiation which our eyes are sensitive to. Visible light is part of the whole electromagnetic spectrum, which extends from radio through microwave, infrared, and through visible to ultraviolet X-rays and gamma rays. And this kind of gives you the size of the wavelength. So radio is like building size, human size, microwave is the size of a butterfly, isn't that sweet? Visible light, protozoans, ultraviolet is more like the size of molecules. And this is interesting because this kind of gives you a clue why ultraviolet is bad, because ultraviolet has a scale, the wavelength has a scale which is comparable to molecular scales, which means that it can get in there and do some damage. And X-rays and gamma rays as well. We don't want to go there, really. We're shielded from all of that by our atmosphere. If you go out above the atmosphere, space is a very unwelcoming place. And again, all of these parts of the spectrum map onto temperature. From very cold, the 3 Kelvin background radiation of the universe is measured actually in the microwave, really, here, I suppose, all up to about 10 or 100 million degrees centigrade. And when we look at most of the movies I'm going to show, in fact, maybe all the rest of them, we're looking at the ultraviolet and the X-rays, which our eyes can't see, but which we can record nonetheless on detectors not unlike the detectors which are in all of your mobile phones that you take photographs with, but then they are turned into images with false color to represent whatever we want the color to represent. Okay, so let's look at this picture again. There's a sunspot image, and I'm going to, just like Innika did, just to reorient you, step up through the atmosphere. Through the chromosphere of the sun, which is the layer, which is about 20,000 degrees Kelvin. We're heading up in temperature towards about 100,000 degrees Kelvin. And in fact, there's a solar flare happening right there. Just coincidentally, I didn't choose that one on purpose at all. Up to about 0.9 million degrees Kelvin, 1.2 million degrees Kelvin. This is all data taken from the Solar Dynamics Observatory, which Innika spoke about too. It's a satellite which is basically returning data at the rate equivalent to 10 terrestrial digital television channels. An unbelievable amount of data. Nobody can possibly watch it all the time. Here, we're looking at the X-rays, pretty much, not quite X-rays, but pretty much X-rays. And as has been pointed out before, where the magnetic regions where you get these enormous brightenings in the atmosphere of the sun. Okay, now, movies is where we have learned ever such a lot about solar activity. I have to say that when the Solar Dynamics Observatory was launched, I thought, oh no, not again. Not, same old, but just more of it. How wrong was I? By by having this 24-hour-a-day view of the atmosphere of the sun, of the entire atmosphere of the sun, not just a little bit and not just occasionally, we start to see connections between different regions on the sun, which we, maybe had hints of before. But now we see as clear as day. We can see that every part of the solar atmosphere is talking to every other part of the solar atmosphere. When an event happens in a region, the rest of the field starts to shake. Communicating by magnetic waves, actually. We've heard about sound waves, but a magnetic field, actually I have my prop here. There's my prop. It's a rubber band. A magnetic field actually behaves a lot like a rubber band, and I can twang it. I can send waves along it. And the atmosphere of the sun is communicating across its volume or through its volume with magnetic waves. Now, this movie, which is about 2 days of real time again, it's enormously speeded up, looking at about 1 million degrees centigrade, the gas, or the plasma, in fact, contained an eruption. You saw it there. In fact, you didn't see the eruption, but you saw that the corona kind of went to let it out. And you'll also see small brightenings and sometimes large brightenings as well. The whole thing is incredibly dynamic and just gives you a sense, even if you don't understand the reason, it gives you a sense of energy. You could just watch these forever, actually, and look at all this funny little stuff happening here and there. People will make their entire career looking at these little whirly things up there, for example. In fact, one of our PhD students is doing just that. We call them solar tornadoes, and he's studying solar tornadoes. So just imagine how many PhD theses there are in that set of data. Okay. This one, if it runs, shows a flare and a coronal mass ejection. So that's the whole disk of the sun, just sitting there being the disk, and suddenly that happens. This actually indicates one of the problems that we have if we want to start predicting solar activity. Before the flare, okay, this is the only big active region on the sun, but not really doing very much. There's nothing to tell it apart really from that region. Maybe it was a little bit brighter, but maybe that's just because it was bigger. And suddenly, it flashes. Now, the flash of radiation is the flare. The associated movement of material is the coronal mass ejection. And sometimes people get the two mixed up. But the flash is really the flare. The movement of material is the coronal mass ejection. And I study flares. I don't study coronal mass ejections. I study flares. I try to understand where the energy comes from to make this intense flash of material, and how the energy moves around through the solar atmosphere, and how it's ultimately dissipated in heat and in radiation that we see. But you'll also see some nice things happening, like when this flare happens, parts of the atmosphere darken. Material goes, well, guess where it's gone? It's gone into space, and this is called a coronal dimming event, and that's part and parcel of the whole flare phenomenon. You'll see that the images are kind of flickering. This is just because they have to change the exposure on the telescope as they make these observations. And you try and correct for it again afterwards, but it's just not always possible. So there's a kind of flickering, particularly down there where the counts are very, very faint. So that's a flare and the beginning of a coronal mass ejection. You can see it doesn't actually occupy very much of the surface of the sun. And indeed, if you measure the total brightness, if you just add up all of the brightness from the sun and turn it into one number and then plot how that varies as a function of time, then in the optical, it's a fraction of a % increase in brightness. Unobservable unless you know what you're looking for. In this part of the spectrum, in the extreme ultraviolet part of the spectrum, you can see it because, well, I think you can maybe even just see how very much brighter this is because it's overexposed. This kind of vertical striping is the detector is saturated. It's overexposed. And so it's very obvious when you look in these particular wavelengths. We'll dig inside an active region. This is actually from the predecessor instrument to the Solar Dynamics Observatory. It was called TRACE, the Transition Region and Coronal Explorer. And this was about its field of view. So it had very, very good spatial detail, but it didn't see much of the sun at any one time. And we've heard about many of these things, these beautiful arches, or loops, as we strangely call them. Loops to me is something that goes round and then comes back and joins on itself, but the terminology in solar physics is to call this a loop. And in here is a sunspot, and in here somewhere is another sunspot. And so the arches are outlining the magnetic field. The magnetic field is a force field. The force field acts upon material which is sensitive to that force field, just like our mass makes us sensitive to the gravitational field of the Earth. We are not sensitive to magnetic fields unless you've got a pacemaker. You don't know about magnetic fields, but certain kinds of material do know about magnetic fields, like iron filings. They know about magnetic fields. They're magnetizable materials, and when you put a bar magnet down in some iron filings, and we used to get to do this kind of stuff at school. I don't know whether iron filings are now considered a health and safety risk, I'm not sure. If you put a bar magnet down in among some iron filings and sort of shake the paper a little bit, then the filings line up along these invisible lines of force. And you can see they're much more complicated than what you might imagine from a gravitational field. If you were to draw the Earth as a circle and draw the gravitational field, it would be a set of lines pointing into the circle, and it would just be spherically symmetric, and everything would point in. But here, the magnetic field goes around, curves back on itself. And the analogy is clear. We're seeing the field outlined by the material which is sensitive to the field, which in this case is the fourth state of matter. It's a plasma. It's a gas which is so hot that the electrons have been stripped off of the atoms, and so it's an electrified gas. And a son of this general part of the world, James Clerk Maxwell, who was also mentioned yesterday, stitched together the laws of electromagnetism. And so with those laws, we can start to understand why the gas is lining up along the magnetic field. So this is a particularly simple example here. Some more complicated magnets. There's two magnets kind of anti-parallel to one another, and there's a null in there. Isn't that beautiful? There's a magnetic null in there. And you can see that the patterns start to get very much more complicated. If you have multiple field sources, you have very complicated magnetic forces. And here is an image taken, sort of turned on its side, because these would be active regions which are lined up along the equator of the sun, but we've turned it on its side for artistic effect. And you can see all of these arches and loops kind of strung out across the equator of the sun. And in the background there is another flare taking place. Set all this into motion, and, well, we've seen plenty of these movies, and again, thinking on the poetic theme, I'm not sure if this is what John Donne meant when he said, "busy old fool, unruly sun." A place of chaos, actually, the atmosphere of the sun is a place of chaos. The different colors tell us about different temperatures of plasma. When it's dark, it's because there's not really much there. The plasma is just leaving and streaming out into the heliosphere. And occasionally you'll see a flare happening and some material streaming out again. So a stunningly beautiful, dynamic place. I appreciate the arts, but sometimes I think we don't really need art when we've got art in nature like this. But, that's after $1 billion and 10 years of work, you get movies like this. And as Ineke said, I don't know what an artist here could do with $1 billion, but I bet they could come up with something to rival this. And as Ineke said, all of this data is available for you on the internet, to download in raw form or in processed form and to play with as you will. Okay, so let's start to think a little bit more about energization. I've got my trusty prop again, my big rubber band. Magnetic fields, particularly magnetic fields when they're embedded in a plasma, are capable of storing energy. And you can do that in two ways. You can stretch it like you're making one of these little rubber band pistols to fire at your teacher or whatever. But you can also twist it, as happens in one of these toy airplanes where you wind the propeller at the front and it twists up the magnetic field, twists up the rubber band. So stretching and twisting store energy in magnetic field. And what's providing the stretching and twisting is, as Ineke was saying, all of the stuff which is happening at and below the surface of the sun, the convection, but also the rotation of the sun. The sun is rotating, and it's rotating differentially, and that stretches the magnetic field and loads it with energy, which eventually pushes up through the surface. So there's a kind of, this is not data, this is not even a simulation, it's just a cartoon, an animation of how the solar rotation winds up the magnetic field. These lines represent the lines of magnetic force, and we lazily call them magnetic field lines, but they're not real, as if they were actual physical things, but they're not. They're a representation of what the force looks like. And the plasma is stuck onto the field, frozen onto the field, we call it. And that means that when the plasma moves, the field has to follow. And so when the plasma at the equator of the sun is rotating a little bit faster than the plasma at the poles of the sun, you can see that the magnetic field gets stretched out, i.e. it gets energized, and also it kind of gets moved upwards into bands to the north and south of the equator, which are exactly where we see sunspots happening. So this picture kind of hangs together, although we haven't really simulated it properly. And then, once the magnetic energy is too high, the whole field goes a little bit unstable, and you get these loops bubbling up into the atmosphere, which are storing energy. Eventually, this energy is released, and that's a flare. And that's a zoom in of a rather large flare called an X flare. Their flares are numbered ABCMX, no, don't ask, from smallest to largest. X flare is the largest, and it's a factor 10 in energy between each of these classifications. So to give you an idea of how much energy we're talking about, the total energy of an event like this is about 1 billion megatons of TNT, or it's about 10,000 times the Earth's annual energy consumption. Or, in fact, this is a number which surprises me because I thought it would be much bigger, but it's not. It's about 10 billion Mars bars, or alternatively, one Mars bar, which is 300 kilometers long, 30 kilometers wide, and 20 kilometers deep. Okay, so there you go. As a flare, and you can see the brightening, the radiation flash, which is the flare, and you can also see the ejection, which accompanies it very fast. How fast? About 1 million kilometers per hour is how fast the ejection is going. And the material which is entrained in the magnetic field, which is moving out into space, is about 1 billion tons, 1,000 million tons of material moving at about 1 million kilometers an hour. And this is why when you see Earth on this, you start to get a little bit anxious. Okay, I think the next slides are just some gratuitous images of flares because there's just so many and they're so gorgeous. This is plasma at about 10 million degrees. It's about the hottest plasma that this particular instrument can detect. And a very ordinary looking active region at the limb of the sun, just sitting there, not even a particularly big one, for some reason decides just to, well, you can see it getting a little bit brighter, and then there's a very intense flash. But this was a flare which had no coronal mass ejection. It was just a radiation flash. Very compact flare, non-eruptive flare, as we call it. Maybe one of the reasons that it was so bright and so very intense at this wavelength is because it didn't spend any of that energy producing an eruption that went into space. It was all dissipated locally, as one speculation. It just looks so sci-fi as well, somehow, with the patterns all over it. I should point out, when it gets going, that you see these crosses on this, and that's not on the sun. That's an artifact of the instrument. It's called a diffraction pattern, and it's there because the telescope, to block out the optical light, has to have filters. Very, very thin metal. The optical light can't get through, but this kind of radiation can get through. But the metals are so thin, the metal is so thin that it has to be supported by grids, very fine wire grids. And in fact, there are 2 wire grids, and they're at slight angles to one another. And when the light passes through those wire grids, it makes what's called a diffraction pattern. And so when you see a diffraction pattern like that, you can tell something very bright has happened. And in fact, if you're so inclined, you can do physics even with the diffraction pattern, and you can work out stuff even from the artifacts on these data. They actually designed it that way so that these patterns were not aligned, so that they were offset from one another, so they could easily be separated out, and they could do this physics. And that was learned from the previous satellite to that, the TRACE satellite, where these diffraction patterns were an annoyance until somebody said, hey, wait a minute, we can work out the wavelength here, because we know about diffraction patterns. So this was designed in this time round. Aren't engineers clever? Okay. Yeah, that's what everybody sees when they see that. Whoa! So I remember I was just saying to Inika over lunch, I gave a talk to the Airdrie Astronomical Society. Airdrie is in North Lanarkshire. It's a not particularly prosperous part of the world, but they have a wonderful astronomical society, a very close-knit group of enthusiasts from school kids up to people who look like your granny, but know a lot more than you ever will. And I was given this talk, and spontaneously from the audience, a 7-year-old boy, or 8-year-old, something like that, said, it looks like a giant dragon spitting fire, is what he said. And I think people's impressions of what they see are very meaningful. This is what they remember of the universe around them. What we're seeing here, again, it's a flare and a coronal mass ejection, but the coronal mass ejection doesn't escape. It's not going fast enough. It's not got enough velocity to escape the high enough speed to escape the gravitational field of the sun. And so it turns around and it plummets back down to the solar surface. It doesn't plummet back down like, if you were to throw a ball, it just goes in an arc. You can see that as it moves through the atmosphere of the sun, it kind of wobbles around sometimes. You see things not going in straight lines, but going in bendy lines, which they wouldn't do if it was just gravity that mattered. They're doing that because the invisible magnetic field is telling them to do that. And another beautiful thing about this observation, I think, is that when you see some of this material hitting the surface of the sun gets brighter. So the story there is that there's magnetic energy, which is transformed into the energy of motion, kinetic energy, which is then transformed into potential energy. As it moves in the Earth's gravitational potential, transformed back into kinetic energy, hits the surface and turned into heat energy. Energy being conserved all the way along, because that's what physics tells us. So you can learn about the ballistics of these things which are hitting the surface of the sun, and the dynamics, and the magnetic field, and any other number of things. And all of this mass comes from a tiny thing called a filament. You can see it just at the beginning, very dark, elongated feature. So Inika, I'm talking about filaments and prominences, an elongated feature in the core of the active region, and that's where we believe the magnetic field is at its strongest. And another gratuitous movie. I don't know, it's like a swan's wings or something. It's absolutely gorgeous. These are 3, or maybe 4 of the filters of the Solar Dynamics Observatory all piled up together. The dark is where material is actually absorbing light from behind it. And if we see dark material like that, we know that it's cool. It has to be cool to be able to absorb material. This is one of Kirchhoff's laws of spectrum formation. Where it's bright along the edges here, there's some heated material as well. And you can see how finely structured and how finely stranded this whole eruption is. I'm sure there's a really good PhD project in working out why it's stranded in that way and what the scale is. And it makes me think of one of those bags that you can get oranges in, and it starts off, all together, and then you kind of pull it apart. And you can also see an unwinding. If you look here, you can see an unwinding. So the field that was previously wound up is now unwinding. And that energy is being transferred into the energy of the eruption. That was mostly an eruption, but here there is a pair of what we call flare ribbons. This was a rather slow flare, but most of its energy went into making the eruption and not so much into the flare, but you can see some bright ribbons spreading out across the surface of the sun. And in fact, by looking at the positions of these ribbons and how they evolve in time, we can start to understand the basic process of energy release. It's a mysterious phenomenon called magnetic reconnection. Okay, more gratuitous movies. Right, so this takes a bit of explaining. This is just a regular movie. You've seen these before. This is called a difference movie, but it's also 3 colors of difference movie superposed. Look here, watch here. So that's the flare that we saw earlier. And if you just look at it in radiation, you can see it, but it's not so, it looks very localized. If you look very carefully, you might be able to see there's a little bit of wobbling going on here. There's a bit of plasma gets cleared out there. But when you do this special processing, you can see disturbances propagating out over the whole surface of the sun. And that's what I mean when I said that my view of the importance of this particular mission changed completely when I saw movies like this. Not only are they absolutely fantastically beautiful, this guy, David Long at University College London, he did a great job in choosing his colour tables there, I think, but they also tell you about the global magnetic effects of these apparently localized disturbances on the solar surface. You can see basically a shock wave which spreads around the surface of the sun. Let's just let it run one more time. So you can see a kind of circular front also propagating out away from the surface. You can see it running over the top of the sun there as well. So really every part of the sun is influenced by every other part in a very kind of holistic picture because of this magnetic field which permeates its entire atmosphere. And then, we've seen this already, and this really segues into what Jim will talk about. We saw there the beginning of the production of a coronal mass ejection, and here we are looking at them propagating out into space. And the distance from the center here to the edge is about 1/8 of the distance to Earth. And you don't get any impression that things are slowing down at all. They're just freely propagating at 1 million kilometers an hour from the sun to us. And if you get an eruption which looks like a circle, I'm not sure there are any in this particular set of movies, then be very afraid, because that's what we call the halo CME, and that's the CME which is coming straight towards you. Or straight away from you. You can't tell because all you see is the projection in 2 dimensions. How am I doing for time? We live inside the atmosphere of a star. This is not to scale, of course, and neither in distance or in size, but it illustrates that the sun's magnetic environment, the sun's radiation environment, and the sun's particle environment influence us. It's a long way away, it's 93 million miles away, but this influence is propagated over great distances by particles, radiation, and magnetic field. And this sketch kind of looks a bit like that, doesn't it? Kind of looks a bit like this. Illustrates the interconnectedness in many ways of these 2 systems. We're surrounded by our own magnetic field, which again Jim will talk about a lot more. It's called our magnetosphere, which is both a boon but also a danger at some times. So, killer solar superstorm could destroy Earth at any moment. scientists warn. It's actually really nice when you look at the proper text, because it's not just scientists, it's shocked scientists warn today that a solar superstorm could destroy Earth at any moment. So from the Express, the Independent, and Forbes. So everybody's worried. And poor Nick Cage. Anytime there's a good disaster waiting to happen, Nick Cage will be in on it. I think this was something about the giant solar flare that was meant to have happened in 2012, which was going to wipe out existence. Is this hyperbole, or is there any truth in it? To our knowledge, it's hyperbole. I'm afraid to disappoint you. People seem to like the idea that there's a disaster looming, known as the EU referendum. We know that there are big flares on the sun, but in our recent history, there hasn't been anything as big as the Carrington flare, the flare of 1859. There's been flares which are bigger in different ways, but not flares which have done the damage that the Carrington flare could have done had it occurred 150, 160 years later. This was the biggest spot group in 25 years, 12192. All of these numbers, they're numbers given to the spot groups by the National Oceanographic and Atmospheric Administration in the US. They do space weather forecasting because people like the military are very keen to know what's happening up there. And this had, it's huge. It's a humdinger, this spot. There's a high-resolution image of it taken from a ground-based telescope. This had 5 major flares, X-flares, tens of smaller flares, no disruption at all. And it was well placed as well to produce disruption, but there was just no disruption. Maybe it just, well, one of the reasons was, for some reason, these flares didn't have a coronal mass ejection associated with them. They were enormous flares, but no coronal mass ejection. Not quite sure why. But so you can get big frightening groups like this on the surface of the sun, but they don't actually do very much. It is something we have to worry about, and again, Jim can say a lot more about that, but some of it now, I think, is an engineering problem. But what about, what if? What if we had something like this, an enormous spot group, an enormous flare, a so-called black swan event? Something which happens rarely, and it happens so rarely that you've no idea how to predict it because we don't have the history, we don't have the statistics to help us predict what's going to happen. Has there been anything like that in the distant past on Earth? Maybe. Dendrochronology. I don't know which is Greek and which is Latin. I think they're probably both Greek. Heliodendrochronology, in fact. These are Japanese cedars. And very recently, people were studying the abundance of different isotopes of carbon. You'll have heard of carbon-14. It's one of the things which is associated with radiation. People talk about carbon-14 as a bad thing. Now, this plot is a year along the bottom, and this is AD year, and it goes 770, 780, 790, 800, and in fact, here's another year, 989, 999, 1009. I have no idea why they did that in nines, but there you go. So these are sort of 10-year intervals, and there are superposed on this plot is the fraction of carbon-14 deduced from the tree rings. And you see that compared to 0, very rapidly that fraction goes up. Within, well, tree rings, the trees grow slowly, you sample 1 year at a time, but within 1 year, the fraction of carbon-14 went up by, well, this is parts per mil, so it's about 1.5%. Very fast, much faster than any kind of terrestrial process would allow. And the thought there is that, well, it could have been a distant supernova, but maybe more likely is that this carbon-14 was produced from processes happening on the sun. For example, an enormous flare. Enormous flares accelerate particles, and we saw that in Inika's movies where you saw all that kind of snow all over the images. They accelerate fast particles. Some of these particles enter our atmosphere. They produce neutrons. The neutrons are captured by nitrogen, of which there is a lot in our atmosphere, turn into carbon-14, make it to the ground through rain or whatever, and are absorbed by the plants and stored there. And so it might be that what we're seeing here is evidence of solar superflares. Who knows? The sun, as I mentioned, if you measure in optical, if you just look at the integrated brightness, the total brightness from the sun, does give a small brightening, 0.02% brightness increase. Kepler, and again, Yvonne mentioned Kepler as being a planet hunting mission and also now an astroseismology mission, but also a stellar flare mission. Kepler can measure the intensity variations of the stars very, very precisely. Now, what's the flare in that? The flare is this narrow spike here or that narrow spike there. This up and down is, well, actually, we're not quite sure, but we think it's probably to do with enormous sunspots on the surface of the sun, of star spots on the surface of the star rotating around. And that's quite unlike the light curve from the Earth, which would be on this scale would be it's quite unlike the light curve from the sun, which on this scale would be completely flat. So this is what I meant what Ineke was hinting at when she said that, well, maybe our sun is actually a rather special sun-like star, in that it's actually quite quiet magnetically and its flares are really rather small. These flares occur on apparently very magnetically active stars. We see the fluctuation telling us about this. And this is a 1.5% brightness increase, so it's 100 times bigger. 8% brightness increase, maybe 1,000 times bigger. So these really are superflares on sun-like stars, stars which have the same mass, the same temperature, the same luminosity, the same rotation rate as the sun. So they're like the sun to all intents and purposes, but much more flare active. And what does that do to the planets in the Goldilocks zones, in the habitable zones? Well, we don't know. But here's an artist's conception of Kepler 438b, which was one of the planets in the Goldilocks zone in Yvonne's talk. And it is a very flare-active star. Its planet is close in. Probably the ultraviolet radiation from these intense flares is changing the chemistry of the atmosphere of the planets. The mass ejections are compressing the planet's magnetic field, if they have any, and stripping away the environment, and probably altogether it's not really a very happy planet to live on. Okay, so I think that's all I really wanted to say. Exit pursued by a flare, excusing apologies to William Shakespeare. Thank you very much for listening.
Thank you very much, Lyndsay, and thank you also for some wonderful pictures. We have time for a few questions, if there are.
Lyndsay, that was, I loved your metaphor of the sun talking to itself as a whole. That's been said about sandpile theory, by the way, you know. But it's a magnificent metaphor, I think, and explains so much that I didn't understand before. I wondered, the speed of a flare, the speed of a coronal mass ejection, are less than the speed of light. So how many minutes does that give us warning before they hit us? Okay,
yes, good question. So the question was about how much warning do we have about coronal mass ejections? Well, the light, first of all, as Charles said, the light travels to us very fast. It takes only 8 minutes for the light to reach us from the sun. And so if we see a flare, you know, there's warning number one, something might have happened. The coronal mass ejection takes between, I think, 18 hours and 36 hours, something like that, to make it to us. And we can track the inner portion of its trajectory. We can see in these coronagraph movies, we can see it leaving And so, we have a decent warning system, but there's one problem. The important property of the coronal mass ejection is not its mass. In fact, coronal mass ejections are completely misnamed. They're chromospheric magnetic ejections, which is also CME, but there you go. It's the magnetic field. It's the magnetic field which is the important property. And specifically, it's the orientation of the magnetic field with respect to the Earth's magnetic field. If the Earth's magnetic field is pointing, I forget, I think it's going north-south right now, I'm not sure. And the CME magnetic field is pointing in the other direction. When they meet, something bad's going to happen. If they're parallel, well, that doesn't happen so quickly. If they're parallel, then the magnetosphere just gets a wee bit compressed and nothing really bad happens. And the one thing that we can't measure right now is the direction of the magnetic field in space. We need to have like a fleet of spacecraft through, like space boys, through the heliosphere measuring this. So we can tell that CME is on its way. There are mathematical models which predict its trajectory, but what we can't tell is this really important property of the direction of its magnetic field.
Time for some fun. Here's a really Scottish question.
Good.
How many litres of fat would it take to deep fry the giant Mars bar? You don't need to answer that. But I'll give you a more serious one.
Sorry, I don't know if everybody heard that question. Did everybody hear that question? How many litres of fat would it take to deep fry the 300-kilometre wide Mars bar? Yeah.
But I suppose, we saw the events in 1859 where the telegraph keys were exploding and whatnot. What effect, is there any effect that a massive flare ejection now would have on our current technology?
I am going to refer that question to the next speaker, whose talk will really go into that in some detail.
Fine.
The short answer is potentially yes.
Right.
Yeah.
Thank you. Sorry for my accent. Two very quick curiosities. You said that flares are different from coronal mass ejection, and that we can observe the flares with no ejection. And the other way around, so can we see ejection of mass without flares? Yes. Okay.
Yes. So the question there was, we can see flares without coronal mass ejections. Can we see coronal mass ejections without flares? Yes, we can. Now, the facetious answer to that is when the flares are occurring on the far side of the sun, and we can't see them. But the sensible answer to that is that there are kinds of flares. In fact, in the sequence of these flares here, there was a flare called a Hyder flare. And a Hyder flare is a flare which occurs in a very weakly magnetized part of the sun. And so you maybe see a little tiny increase in the X-rays and a little perturbation on the surface of the sun, but you can get a beautiful coronal mass ejection from it. And also from the north and the south regions around the north and the south pole of the sun, there are features called prominences, and Ineke showed some computations of where prominences are, filaments are, and sometimes when they lift off, they make a CME, but there's really no flare signature at all. So there is a puzzle there. What decides how much energy goes into making the flare and how much energy goes into making the CME? And we're not close to solving that yet.
The second one, are the flares generated on the surface, or they're creating a more internal part of the sun and then migrating to the surface?
Okay, so the question there is, are the flares created on the surface or underneath the surface and popping up? The radiation flash and the energy storage come from just above the surface, about the first 10,000 kilometers. We can image that very well, and we can not measure the magnetic field stresses, but we can calculate the magnetic field stresses. So we're fairly sure that the instant of flare energy release happens above the surface. The energy ultimately, though, came from below. So it was produced. It's a beautiful holistic picture of a rotating, convecting star where energy is being pumped into this magnetic field, which is feeding up into the atmosphere, and then bang, it goes, and we see the visible effects of it.
Thank you very much.